As you know, nuclear fusion is taking lighter elements and putting them together to create heavier elements, or at least it's exothermic when we fuse up to the element iron. It's actually possible to fuse heavier elements to even heavier elements, but as we get heavier elements, they tend to be less stable and require the input of energy. I'm going to concentrate here on mainly that light element fusion. Talk about, first of all, how elements were fused early on in the universe. Talk about the fusion in stars. Talk about, unfortunately, the use of fusion in thermonuclear weapons. Then finally, the commercial applications or potential commercial applications for generating fusion energy in the future. So let's first of all begin with fusion. We fuse lighter elements into heavier elements, and we know with the strong force that as we increase the binding energy being a negative energy, we can liberate energy in the form of heat, making this reaction exothermic. So looking at fusion, we actually can see that fusing hydrogen into helium is very, very strongly exothermic, which means we release a tremendous amount of energy per nucleon in these fusion reactions. The binding energy of a free proton, of course, is going to be zero because there's no binding force to a free particle. And the binding energy for helium-4 is 7 megaelectron volts per particle or per nucleon. So again, the fusion of hydrogen-1 into helium-4 is highly exothermic. When we compare this to fission reactions, clearly fusion liberates a much larger amount of energy, even though fission is many more times energetic than chemical exothermic reactions. Fusion, again, is, looking at this, approximately 7 times more energetic when we're fusing the lightest element, hydrogen. So once again, there are 4 places where fusion is very, very important. One, of course, was the beginning of the universe. The second was the fusion in stars, and still remains the fusion in stars. We're fortunate that we have a huge fusion reactor at the center of our solar system, powering energy on Earth. An unfortunate aspect of fusion is, of course, thermonuclear weapons, which are far more destructive than the fission weapons that we talked about in the previous section. Finally, our hope for the future is to power our energy needs with fusion reactors. However, we're finding that fusion is always just a couple decades away. And that's sort of the joke about it, that as time goes by, we don't get any closer to it. But we'll talk about that and discuss some of the challenges. So first of all, let's talk about the first nuclear fusion that occurred. When the universe first formed, very, very early on, from about the first second to the first few minutes, probably about 30 minutes, the universe was cool enough for nuclei to come together. Before the first second, the temperatures were just too high that any nuclei that formed would have ripped apart. But after the first second, up until about the first half hour, the universe remained hot enough and dense enough for hydrogen to fuse into heavier elements, because at that point, quarks had come together to form protons and neutrons, and then the protons and neutrons could, of course, fuse together to produce heavier elements to about lithium. So it converted about 1/4 of all the hydrogen into helium, small fraction into deuterium, and an even smaller ratio into lithium. And essentially that became the building blocks for the universe from that point on. So when we look at our universe today, the chemical makeup still remains fairly close to this ratio. Obviously, with the nucleosynthesis in stars, we've seen more and more heavy elements being created, but we're still pretty close to the fraction of 3/4 hydrogen to about 1/4 helium. Now, the second example fusion is, of course, with stars. And what better example of a star to use than our own sun? We look at the sun, and it's really the greatest source of energy for our solar system. Most of our energy is directly linked to the sun, although there's some geothermal energy, which is related to radioactive decay. But again, the sun is the most important source of energy, and certainly the most important source of nuclear fusion for us. As young stars get older, they generate more and more fusion products. First, it's helium, and this builds up in the core. And then after enough builds up in the core, we'll see that they become giant and supergiant stars. How does fusion occur? It's different from fission. With fusion, we need very, very high temperatures. We need fairly high densities. The reason is when we take a nucleus apart, when we have fission of uranium or we have fission of plutonium, the forces that are involved are really coming from the Coulomb repulsion within it. So the force is already present no matter what the temperature is for these very heavy nuclei. And of course, the uranium and the plutonium will spontaneously undergo fission without any temperature reliance. Okay. Now, if we reach a high enough temperature, yes, fission would become more and more likely, but we're talking about really high temperatures before the thermal energies come into play into fission. So fission can happen at any temperature. Fusion, this is different because we're trying to bring two positively charged particles together. In order to do so, we have to overcome that Coulomb barrier, that barrier of energy to get them to merge and get that strong force to take hold. So stars generate their energy through nuclear fusion. This provides the heat. Think about the star this way. The gravity wants to crush a star. If there is no source of opposing pressure, the star would just keep crushing itself until it reached what's known as its electron degeneracy state. Basically, the electrons would be pushed as close together as possible, and only the degeneracy pressure would prevent a further collapse. However, with a star, by definition, a star is undergoing fusion in its core. And this fusion generates heat. The heat generates pressure. The pressure opposes gravity. So essentially, during the entire star's life, it's going to be an outward force from heat, mostly generated by fusion, and an inward pressure from the gravitational forces. And the temperature must be high enough to basically support the weight of the star. Otherwise, it is going to collapse. The temperature of the sun, its core, is between 10 million and 16 million degrees. Basically, if we take a average over the volume, we come out to about 14 million degrees. But again, this is a really, really high temperature necessary because these particles have to have enough kinetic energy to overcome the potential energy. And that really, we look at the Boltzmann distribution, and to even get a small fraction of the particles to overcome this Coulomb repulsion, we've got to be over 10 million degrees. So in terms of the sun, there are different types of hydrogen fusion that takes place inside different stars. The proton-proton cycle 1 is, I guess, the most technical name for what happens inside our sun. There's actually more than one proton chain, proton-proton chain 1. But the one that we're going to talk about, the one that is most common in the sun, is where hydrogen fuses into deuterium. Deuterium fuses with hydrogen to become helium-3. Helium-3 fuses together to become helium-4. So this is a multi-step process. And the hardest of the reactions to start, where we have the most energy that we need to overcome, is the initial fusion of hydrogen. Deuterium hydrogen is actually easier, so is helium-3, until finally making helium-4. So we start out with two protons coming together. The protons merge together to form a proton and a neutron, but the neutron has to be created from one of the protons, if you want to think about it as simplistically as possible, meaning that in addition, a positron is given off, and this also gives off a neutrino because a positron is an antiparticle, and it's also an anti-lepton. We need another lepton to balance this. So that's the basic reaction. So during this reaction, the positron is going to be created. It's probably going to annihilate fairly quickly with some free electron, and this is going to release more energy in the form of gamma rays and help support the star's inward pressure. The next step is, again, hydrogen with deuterium. This time, the only final product here is helium-3. Now, helium-3 is a rare isotope of helium where we have two protons and only one neutron. Whereas in the previous reaction, we released about 1 megaelectron volt per nucleon. Here, we're releasing about 1.5 mega electron volts per nucleon. The final and the most energetic of the interactions is the fusion of helium-3 with helium-3. This results in helium-4, but it also releases two protons because the helium-4 is very, very stable. You're closing the proton shells, you're closing the neutron shells, and it's just more stable for this to result in helium-4. I mean, the alternative is if it got two protons, it'd be very unstable. It'd be, I guess that would be a carbon. No, it wouldn't be carbon. We're looking at a form of beryllium, beryllium-6, and that's just not stable. So looking at the different steps, this is the best way to visualize it. Protons fuse with protons to create deuterium. Deuterium fuses with protons to create helium-3. And then your biggest step, your biggest increase in energy, going from helium-3 to helium-4, and also releasing two protons, which can then participate in further reactions. And again, in terms of the binding energy per nucleon, you're going from 0 to 7 megaelectron volts per nucleon. We're not that far from iron at about 8.5 megaelectron volts per nucleon. So again, hydrogen fusion, highly energetic, highly exothermic in generating energy. So our sun has been fusing hydrogen in its core for about 5 billion years. And fortunately for us, this reaction will continue for about 5 billion more years. In terms of conditions on Earth, the sun, unfortunately, even if we control the greenhouse effect, the Earth is just going to get hotter because as the sun's core gets heavier, it shrinks and gets hotter. That causes the outer parts of the sun to actually expand. But it will continue to fuse hydrogen in its core for about 3 billion more years until the core shuts off. And basically, this is going to create a very big transformation for our sun, which has been fairly stable in terms of its energy output. When this happens, the helium that's collected at the center begins to contract. And initially, most of the sun's energy is not going to come from fusion, but it's going to come from the shrinking of the sun's core as it goes from a main sequence star to what's known as a subgiant. Eventually, it completely transforms to a giant star, at which point the hydrogen around the core forms a new place where fusion can happen. And basically, it has to produce enough heat to keep the helium core hot enough from collapsing further and keep the outer layers from collapsing inward. So in a sense, what happens is this what we call the shell burning, this hydrogen fusion in the shell, generates far more energy than the sun needs to prevent the outer layers from collapsing. So the outer layers will basically puff out, turning our star from a normal star to a giant star. And at this point, the sun is pretty much running into its last 1 billion to 2 billion years left of its life. Won't be a good situation for us. The surface of the sun will expand outward, but an even bigger problem is the fact that the solar wind is going to become very, very strong. So we can't really imagine that the Earth is going to be hospitable at this point, because it's going to shed atmosphere. An intense solar wind is just going to rip off any atmosphere that the planets have in the inner solar system. The surface of the Earth will become essentially hot enough to melt rock, and life will have long ceased to exist on Earth at this point. Now, once again, the shell has to produce more energy than is necessary. And what happens is the core of the sun actually gets hotter than it is today. Right now, it's around, between 10 and 16 million degrees. But it's going to get even hotter because, again, it's not heating that helium center very efficiently. It has to heat it from the outside in. And that means that the temperature is going to jump dramatically. And another type of fusion becomes favorable. And, we oftentimes just learn hydrogen's fusing the helium, and that's the end of it. This is actually a catalyzed type of fusion, which happens when hydrogen fuses with carbon-12. Hydrogen fuses with carbon-12. This becomes nitrogen-13. The nitrogen-13 decays by beta plus to become carbon-13. The carbon-13 fuses with a hydrogen to become nitrogen-14. The nitrogen-14 fuses with hydrogen again to become oxygen-15. The oxygen-15 then decays by beta plus again, and then that becomes nitrogen-15, which fuses with a proton. And at this point, we get it unstable enough where it gives off a helium nuclei and goes back to being carbon-12. So you see here that carbon-12 has really become a catalyst in this reaction. It returns to its original state, and we put in 1, 2, 3, 4 hydrogen, and we get out 1 helium. So the end result is the same. Energetically, it's pretty much equivalent to the PP chain. But again, unlike the proton-proton chain, in this case, this is catalyzed by the presence of carbon. It's just energetically favorable at these higher temperatures. So the core continues to grow. We're building up waste, okay? Basically, anytime you have a reaction, you have reactants, and then you have products. The products of hydrogen fusion is helium. Helium is heavier than hydrogen. It accumulates in the core, making the core heavier, making the core denser, and making the core hotter. Eventually, the core reaches over 100 million degrees Kelvin. At this point, we have enough energy where the helium can begin to fuse. Now, I always, when I teach astronomy, I always like to, talk about what happens on the inside is opposite of what happens on the outside. If the core shrinks, the outside expands. If the core expands, the outside shrinks. At this point, the core suddenly turns on. It's no longer hydrogen fusion in the shell. The core turns on, and we get helium fusing into a heavier element, in this case, carbon. Well, that makes the core now no longer heated from the outside, but heated from within. So it expands. The outside of our sun would actually contract. It would become a horizontal branch star. Due to its metallicity, it might be classified as what's called a red clump star. But with fusion happening in the core again, the star actually shrinks and becomes more efficient. So here's a strange problem with helium fusion. When helium fuses, we think that, okay, helium's going to fuse with helium. We're just going to get something from 2 helium that's going to be heavier. Beryllium-8, of course, seems to make sense. Problem is, beryllium-8 is very unstable. So when helium tries to fuse into beryllium, the beryllium just falls apart. That's why we need these really, really high temperatures, because you need the helium to fuse together to produce the beryllium. But before a decay can happen in the beryllium, it's got to fuse with another helium. So it's got to be boom, boom, 2 reactions happen almost instantaneously, and then you can get to the more stable carbon-12. Remember the shell model, and we said beryllium-8 is not stable because really beryllium-8 is 4 protons, 4 neutrons. It's very easy for that beryllium to drop down and fill that lower shell by dividing into helium and helium. So carbon-12 is more stable, but it requires the input of 3 helium nuclei instead. Now, here's a problem, and this is why at this point in a star's life, and this point in the sun's life, time to the next phase is becoming less and less. And the reason for this is we don't get as big a bang for our reactions, meaning that when we fuse helium into carbon, we get less than 1 mega electron volt per nucleon, whereas we got 7 before. So it means that it has to fuse helium at a much higher rate, and that means it's going to use up the fuel in its core much quicker. It's going to be at the state in a much shorter time. Yeah, it took 10 billion years for it to run out of hydrogen in the core. Now it's going to take a much shorter time to run out of helium in the core. And at that point, when it does run out of helium, essentially the star is going to end its life, and it's going to contract. The core is going to contract to become a white dwarf. The outer layers are just going to blow off into space. Now, the problem is at some point, the helium fusing creates carbon, but the carbon actually begins to fuse with helium to produce oxygen, and even the oxygen fuses with helium to produce neon. So we've got a collection of things going on in the core. But again, you're building up this inert core at the center, and the helium begins to fuse erratically, and oxygen is produced. I guess the best way to talk about this is that the asymptotic giant branch star, where the sun is at its largest, it's at the end of its life. The core is very unstable; it's almost pulsing. And instead of this nice continuous output of energy, at its very end, these pulses are basically blowing off layers of the outer star, so there's nothing left but a core, and this, of course, is a white dwarf. The neat thing is that as this is taking place, these pulses of fusion are taking place, the outer layers are being ripped off. We also begin to generate some unusual elements. Basically, we call this the S process elements, slow neutrons. The fusion that is taking place is just generating a lot of neutrons. These neutrons are being absorbed by different nuclei, and we're just moving up. You can see this. We're actually moving up the periodic table. So for instance, if we're up to silver, we can add a neutron. Actually, silver beta decays into cadmium. Cadmium keeps adding neutrons until that becomes unstable, comes up to become indium, then indium decays to become tin, then tin becomes antimony. You can just see it's climbing up the ladder. This is not a very common reaction that's taking place, but what we're doing is we're filling up the periodic table of elements. So, our universe is a little more interesting than just hydrogen, helium, carbon, oxygen, and neon. But again, This reactor is very, very temperamental, blowing out its outer layers into space, forming a very beautiful planetary nebula, and then leaving a white dwarf behind. So this is basically the life cycle of a star like our sun. And it explains why we have more than just hydrogen, helium, and a little bit of lithium in the universe. We do get some of these heavier elements from stars like our sun, but it doesn't answer all the questions. This periodic table here shows the low mass stars like our sun. Again, a lot of carbon is produced in this process. Let's take a look at, unfortunately, I'm hiding oxygen. Neon is also being hidden in here, but we're just building up to heavier and heavier elements through this S process. And you can see here some of these, this green right here indicating those elements just being built up with neutron after neutron. All right. But by far, filling out the periodic table of elements, many of the elements are not created in high proportions in our sun. They have to be created in even more massive stars than our sun. And the reason for this is, at the end of our sun's life, there's not enough gravitational pressure, putting a lid or holding down this core, which is just pulsing. If the sun were more massive, that pressure would keep the reactions more stable. One of the problems is you get a lot of it'll pulse, then become degenerate, pulse, and then become degenerate. In a more massive star, the pressure keeps on the core, the temperatures remain higher, that we never reach this degenerate state. And it just keeps going from a lighter element to a heavier, to heavier, to heavier, on and on and on. So let's take a look at the life cycle of a massive star. Just like our sun, it'll start fusing hydrogen into helium. When enough helium is built up in the core, the helium is fused into carbon. So the story is pretty much the same so far. But when enough carbon and oxygen form in the core, temperatures get hot enough. This doesn't happen in our sun, but temperatures get hot enough where this core suddenly turns on and begins to fuse into heavier elements than carbon. So what happens is the carbon fuses to produce oxygen, neon, and magnesium. Got to be more than about 8 or 9 times the solar mass. And we just keep making heavier and heavier elements. And we can continue to do this all the way up to iron. So for instance, once the core of the star reaches 500 million degrees, something our sun's not capable of doing because its mass isn't high enough, carbon will fuse to become neon, sodium, and magnesium. Okay, so neon, sodium, and magnesium. And that after the carbon is used up in the core, okay, after carbon fusion has taken place, we begin to fuse oxygen and neon. So for instance, oxygen fuses with itself to become magnesium, silicon, which is very, very important because for the end of the reactions, phosphorus and sulfur. After the oxygen fusion is turned on, silicon fusion will turn on, but here's the rub of the whole thing. Okay. Stars spend most of their lives fusing hydrogen into helium, okay? 90% of their life, hydrogen into helium, okay? It's that last percentage, okay, of its life that it's going to fuse the heavier elements. And each heavier element represents a shorter time because the core is becoming denser, it's becoming hotter, it's requiring more energy to support itself. We're getting less energy from the reactions. Remember, hydrogen fusion, we get about 7 megaelectron volts per nucleon, and then we jump to helium, and we get less than 1 as we fuse to carbon. Carbon produces even less energy. So again, looking at the fusion times, really, in terms of carbon fusion, the star probably only has maybe 100 years to continue, maybe a little bit longer. Maybe it's oxygen fusion that takes place over a short period of time, but the times are getting shorter. Then we jump to additional fusion, where we only have about 6 months to go before we've used up all of the oxygen and neon. And after the oxygen and neon fusion are done, silicon fusion only happens for a few days. Okay? The star has been around, not as long as our sun, because very massive stars fuse for a much shorter amount of time. They need more energy to hold themselves up. But for a star that's been around for tens of millions of years, perhaps, okay, on its last couple of days, it's fusing silicon into iron, and it's basically poisoning its core. Now, why can't it fuse iron? Well, what happens is if it fuses iron into heavier nuclei, that's endothermic, okay? Hydrogen fusion, exothermic, it supports the star. Helium fusion, exothermic, supports the star. Carbon fusion supports the star. Oxygen fusion, not much energy, but it's still going in to support the star. Silicon fusion, so little energy that it's just enough to hold the star up for a few days. But as soon as it starts fusing iron, that sucks energy. And you think, well, this is a slow process. This core is huge. But actually what happens is when the iron core gets so heavy and so hot, where the iron nuclei start fusing, okay, it collapses nearly at the speed of light. So it's literally like standing on a stool and somebody pulling that stool out from under them. The whole star comes crashing down on the core, and that leads to a supernova explosion. So again, looking at the yield per reaction, hydrogen fusion, the reason why the star spends so much of its life fusing hydrogen is it's a very efficient fuel to support the weight of the star. Helium less so, carbon less so, oxygen less so, silicon even less so, okay? But iron, that's your dead end. When it fuses iron, the iron core is going to collapse. It's going to collapse nearly at the speed of light. Once the degeneracy pressure of the nuclei, I'm sorry, not the nuclei, the electrons. Once the electron degeneracy pressure, when the electrons are so tightly packed, they can't get any tighter. All right, I said the ions fuse, but in actuality, what's happening here is the electrons are packed so tightly that they merge with the protons. And this creates a collapse nearly at the speed of light. The whole iron core disappears into a ball of very heavy nuclei and neutrons, thus the name, it leaves behind a neutron star. But the good news is, as the core collapses, all the other elements which were trapped inside the core are suddenly released in this huge explosion known as a supernova. And this just becomes a really big source of heavier elements. So let's wind back a little bit, back to our little chart of elements. And we see here explosive massive stars. Where are the majority of the elements produced? Quite a bit of carbon, nitrogen, oxygen. All of these are being released from the center of the star. Take a look at this. The center of the star, and they're being blown out into space. Now, there are two important other things. I don't want to get into too much astrophysics here, because I think I spent a lot of time doing this. But there are two other very important processes by which we can generate other nuclei. One, a type 1a supernova is a white dwarf, which is basically a vampire. It takes mass off of another star, and then it reaches a critical mass. Okay, it's mostly carbon. What a white dwarf is, it's mostly carbon. And it undergoes a rapid fusion explosion where it just blows itself out of existence and blows rapid fusion reaction, releasing all these elements that you see here in gray. Okay, so silicon, sulfur, chlorine, argon, potassium, calcium, scandium, exploding white dwarfs, type 1a supernova are responsible for a lot of that. But if you look at some of these transition metals, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, they all come from these exploding white dwarfs. Okay, now why are elements such as silver, gold, platinum just so expensive? Actually, iridium, osmium, and rhenium are also very, very expensive. I don't know if you realize this, but rhodium is probably more expensive than gold. These are rare elements, and they come from neutron stars that merge together to become a black hole. But as they merge, they spin off some very rare elements, and that fills up a lot of the rest of this periodic table. So, yeah, that's next. We have these exploding stars, which are really so key to life here on Earth. These supernova, be it an exploding supergiant star like the one we talked about, be it a type 1a supernova, like a white dwarf orbiting another star. Think about the Earth. The most common elements in the Earth are iron, oxygen, silicon. All of these come from these exploding supernova stars, which send this matter back into the universe after the star is done with it. All right, they weren't created at the beginning of the universe. The universe only had hydrogen and helium. Our Earth is here today from the fusion that takes place in these exploding stars. Well, human beings, unfortunately, have this tendency to take any technology and somehow convert it into a weapon, and thermonuclear weapons are no exception to the rule, where we try to take the fusion reaction from the inside of a star and turn it into a vast source of destructive energy. So the first thermonuclear bomb was codenamed Mike, and this was developed. Just amazing how quickly we went from the 1940s, 1945, we have the first fission bomb. In the 1950s, we have the first fusion bomb, or thermonuclear bomb. The reason why we call it a thermonuclear bomb is we use the energy, thermal energy, from a fission reaction to power a fusion reaction. Now, basically, we are taking the nuclear fusion reaction of deuterium and tritium rather than hydrogen, because it's an easier reaction to run. It takes less heat and energy to initiate that reaction. But it's essentially the same thing that's happening in the middle of our sun. We're converting hydrogen into helium and releasing a large amount of energy. Now, this is what's known as the Teller-Ulam device. And again, it is a fission bomb that is the trigger. So at one end, we have this plutonium fission bomb. And when it detonates by implosion. We talked about that in the previous section. And as it detonates, it is going to produce a very, very hot fireball, okay? Initially, the temperatures are in the millions of degrees, so it's shining very, very brightly in the X-ray part of the spectrum. But the problem is this fireball is expanding and is destroying the weapon in a very short amount of time. So we initiate the fission bomb first. The fission bomb explodes first. And as it shines, the X-rays are sent down this, you can imagine this is like a cylinder with this hollow channel that allows the X-rays down the channel, but yet there's a big plug of heavy material which temporarily blocks the fireball from coming forward and temporarily shadows the device so it doesn't directly get the X-rays and just vaporize. But the X-rays travel down this hollow channel, they radiate inward. Now, if you think about the way a rocket works, a rocket is action-reaction. The hot gases are pushed downward to send the rocket upward. In this case, the X-rays superheat this material on the surface of this bomb. Okay, basically, it's what's called a pusher. This very hot this material will become very, very hot. And as the surface is vaporized, it's like rocket thrust, just pushing the whole, crushing the whole cylinder inward. And first of all, the primary X-rays vaporize and ionize polystyrene, producing a secondary plasma. This secondary plasma shines its own X-rays, focusing on this pusher material, okay? And then that's going to crush this deuterium and tritium. So the pusher begins to implode inwards, crushing our fuel. The deuterium, due to adiabatic compression, is getting extremely hot. Anytime you compress something, you can drive the temperatures to a very high temperature. And at the same time, the deuterium tritium fuel is also pushing on the center. Actually, it's mostly deuterium. Tritium will be created by the center, what's called a spark plug. This is typically made out of fissile material, which gives off a lot of neutrons. The neutrons convert the deuterium into tritium, and all of a sudden you've got a deuterium-tritium reaction happening at the center of it, and this 20 kiloton plutonium trigger, which started the whole thing off, has now been amplified by a fusion reaction, which is many times stronger. So for instance, we go back to Mike, which is the first thermonuclear bomb, that the 20 kiloton plutonium device triggered a 10 megaton, okay, or 10,000 kiloton fusion reaction. So as devastating as these plutonium bombs are, their energy is used to create an even more energetic fusion reaction. And again, here is a very, very famous fireball that we see from these types of events. It produces a mushroom cloud. That's due to convection. The hot fireball becomes unstable, begins to rise, and as it does so, it starts to convect into this torus-like structure, and just simply rises due to buoyancy. Now, modern thermonuclear weapons are not quite as strong as Mike was. They're designed to basically be more compact. We're not happy with just sending one nuclear warhead on a single missile. We actually pack these missiles with many warheads, and these MIRVs, these multiple individual reentry devices, will actually target different locations. So with one missile, we unfortunately have the capability of destroying many different places. So again, we use fission reactions to detonate a larger fusion reaction, and it can be hundreds, if not thousands of times bigger than the bomb dropped on Nagasaki. And theoretically, you can make a thermonuclear bomb as big as you want. The Russians created the Tsar bomba, which gave a yield of 50 megatons. If they equipped it with an additional fission layer, it would have been capable of 100 megatons. So, at that point, it just becomes ridiculous in terms of the explosive power that these weapons have. And hopefully, we will continue to decrease the availability of these weapons. On the good side, we might someday be able to use fusion in terms of constructive purposes for the generation of electricity. Fusion reactors, however, remain very, very difficult. Fission, again, happens under the right conditions, independent of temperature, but fusion, we need really high temperatures in order to achieve a reaction. This creates the biggest problem, which is, how do I take something that's 100 million degrees Kelvin and hold it so the reaction can take place? Okay, what we call confinement. Physical confinement is not possible with this. I can't hold the plasma here because two things are going to happen. One, the plasma is going to heat the walls of the container, basically vaporizing them. At the same time, the plasma is going to give up its energy and cool as it comes in contact with the chamber walls. So how do we keep the plasma in place without physically touching it? And basically, there's two different ways of doing it. There's inertial confinement, there's magnetic confinement. Okay, so good things about fusion. First of all, hydrogen is readily available. We can get it from water. Deuterium comes about 0.06 grams for every gallon of water. It costs about 4 cents. Okay. Really, during the fusion reaction, if we're careful about what we make the reactor out of, it does produce neutrons. So we've got to be careful that we don't activate different material and make the reactor itself, radioactive. But basically, your waste from the fusion reaction is helium. Okay. So deuterium tritium fusion is different from what happens in the sun. If you remember the steps in the sun, we went hydrogen 1 to hydrogen 1, became deuterium. The deuterium then fused to become helium 3. The helium 3 then fused to become helium 4. Here, we're still at some point using deuterium, but instead of fusing deuterium with hydrogen 1, we fuse it with tritium, hydrogen 3. This results in helium 4 and kicks out a neutron. Okay? Now, it would be so much better if we could fuse deuterium with deuterium, but that requires higher temperatures and higher energies. Hydrogen 1 would be a great place to start out with, but as we said before, in the proton-proton chain, that first step is the hardest one to take. It's always easier to go and fuse deuterium or fuse deuterium with tritium. Okay, so first of all, what we need to do is we need to obtain a source of tritium, because tritium doesn't exist in high quantities in nature. But the good thing is we can actually create tritium. The tritium that was used in thermonuclear weapons, such as Mike, were actually made in breeder reactors. Reactor B actually generated tritium. So we know how to create tritium. All we need is a neutron source. We put heavy water in with a neutron source that generates tritium, and then we can extract the tritium out. So we know how to create tritium. We have the devices to do it. And in fact, once a reactor is working, it generates neutrons. It can be used as a neutron source to generate tritium. So here's why we do deuterium-tritium fusion as opposed to deuterium-deuterium fusion. First of all, it happens at a much lower temperature for what we need it to do than proton-proton. So right off the bat, it's easier to do. Now, you're saying, when you introduced the sun, you said that the sun only needs, about 10 million to 14 million degrees Kelvin in order for fusion to take place. But that's producing very little energy. For every cubic meter inside the sun, this should be cubic meters, by the way, you only get 275 watts, okay? A reactor is only so many cubic meters. If I'm only getting a few kilowatts out of that reactor, it's not efficient. we need to do better than that. So what we can do is we boost the amount of energy we get out by increasing the density and the temperature. There are a few different requirements. There's something called Lawson's criteria that states that for deuterium tritium, we need the density of the plasma and the time that we confine it. Okay. Confinement time is a little, this tau here is a little bit strange because it's actually more about how much energy density we have compared to how much energy we lose. But we need an n tau greater than 10 to the 14. So we can confine it one of two ways. We can trap it in a magnetic field, in what we call a tokamak, or we can basically create a mini thermonuclear bomb. It's not as bad as it sounds, but we can use lasers. Remember, we used X-rays to compress the deuterium tritium fuel in a thermonuclear weapon. We can use lasers to implode a fuel pellet. So let's talk about the inertial confinement, which basically you hit it from all sides. So you take the inertia of imploding material to confine the plasma long enough for fusion to take place. And this happens at the National Ignition Facility. You've probably seen this in the news recently, where they produced more power than they consumed. Okay, just let's be careful with the way that we word this. The lasers take more power to operate than laser power, but we did get more fusion power out than we put laser power in. Now, this thing is massive. It's a huge building with 192 lasers and laser amplifiers. These produce a laser beam or laser beams at the infrared part of light. They then use nonlinear crystals to convert the 1 micron light to ultraviolet light. And why do you want to do that? Because if you remember from optics, how small we can focus this is very much dependent on the wavelength. If we use too large of a wavelength, we can't focus the energy as easily. And also, beside the spot size of the laser, in the ultraviolet, we're going to use the ultraviolets to generate X-rays. And it's a more efficient process going from UV to X-ray than from infrared to X-ray. I hope I'm explaining this properly. You plasma fusion physicists out there are probably cringing about what I'm saying, but the ultraviolet light creates a better conversion. So the UV lasers, and again, more energy is needed this, but they're focused on this container. And this container is called a hologram. I'm just going to say it once because I always mispronounce it. The laser energy is focused on the walls of this chamber, and then the chamber radiates X-rays that compress the fuel pellet, much like the fission bomb and the thermonuclear bomb created fusion. And again, huge building. This is at Lawrence Livermore Laboratory. It's called the National Ignition Facility. And all the laser beams focus onto the pellet. Boom, it's a one-shot deal. So in terms of turning this into a commercial power plant, this would be very, very difficult. We'd have to keep firing the lasers and compressing fuel pellet after fuel pellet. But it allows us to study fusion in these different conditions. And just to let you on a dirty little secret, the main purpose of the National Ignition Facility is not the generation of commercial power, it's to simulate fusion that takes place in thermonuclear weapons. So, okay, not to knock people down at Lawrence Livermore. That's not fair, but I would say much of the funding was geared toward a device that could study the stewardship of our nuclear stockpile, although they do get very important information about fusion from this particular experiment. Now I'm going to get some nasty remarks in my comments. Magnetic confinement is the other approach, but this is also very, very problematic in terms of turning into commercial power. Here's how it works. We want to trap the plasma. The plasma is at 100 million degrees Kelvin. when we want fusion to take place? Well, we know we can trap plasma through the Lorentz force, meaning that we will always have a force on a charged particle if it's moving, which is perpendicular to the direction of the magnetic field, okay? It causes the particles to go around in a circle. So if the particles are moving in random directions, they will maintain a helical orbit around the magnetic field. So the idea here is if we can take the magnetic field and make a closed loop, the plasma will be trapped going around this torus indefinitely, with this magnetic field, pinning these helical trajectories within the container. So basically, we hold the plasma in this toroidal shape, and it's more complex than I'm giving it credit for. We hold it in this toroidal shape, and in doing so, we hold it off the walls of the reactor itself. And here we have the tokamak, which is this toroidal magnetic confinement device for fusion. And it requires very, very strong magnetic fields. And what it also allows us to do is induce currents within the plasma to actually heat it up. So one thing that you'll see when they talk about the quality of fusion reactions is this thing called the fusion triple product. It's how dense you can make the plasma, because the denser you make it, the more reactions you're going to have. There's a minimum temperature. You need to be at 100 million degrees Kelvin for these reactions to happen often enough. And then you need this confinement time, which again is technically going to be the energy density divided by the power. And this was attempted at Princeton, at the Princeton tokamak. It was attempted at the Joint European Torus. And both experiments ran into problems because when you generate a plasma, the plasma is going to interact with the magnetic field. This creates instabilities, and neither one was able to overcome instabilities. If we look at the reactor itself that is being currently constructed, known as ITER, it is, essentially a huge, you see 1 story, 2 stories, 3 stories, 4 stories, 5 stories tall, monstrous device, which is going to attempt to break even in terms of the energy that they put in compared to the energy that they got out. Now, remember, the National Ignition Facility did not end up getting more energy out than they put into the lasers. They got more fusion energy out than the UV lasers put in. And again, if this works, they expect about 410 megawatts of fusion power. This would just be thermal power, where the amount of power that we put in, if I'm reading this correctly, would be anywhere to 40 to 90 megawatts. So ideally, about a quality factor of 10, meaning 10 times more energy out than we put in. Okay. In terms of will this work? Well, this is a really expensive machine that doesn't even generate electricity. I can't say. As a kid, and I'm talking about the time that I was visiting the Princeton tokamak in high school back in the 1980s, to give you an idea how old I am. They were always saying, "Oh, commercial fusion power is around the corner." Well, 1980s, that was a long time ago, and we still don't have a commercial fusion reactor. So, is it 20 years off into the future? I doubt it. Is it 100 years? Maybe, but I may not live to see it. In any case, one other idea for fusion reactors is instead of generating the energy all from fusion, use a lower power fusion reactor, one that doesn't break even but generates a lot of neutrons, and then use the neutrons to create fission within radioactive waste. One of the big problems with radioactive waste is, you've got to store it for a long period of time before it is safe. If you irradiated radioactive waste with neutrons, you could actually transmute some nuclei, or so they say, not me, into something that's a little more safe, okay? That has a shorter half-life and can be disposed of more rapidly. At the same time, you generate energy. So this might be the new type of fission fusion reaction. So, okay,